Interfacing an LLM with a production API requires exact alignment between the model's reasoning and the technical requirements of the tool. Developers typically monitor this alignment through training loss, a metric that tracks how much the model's output deviates from the ground truth during training. However, a low loss score doesn't guarantee logic. A model can master the syntax of an API call while still failing to distinguish between a simple ID lookup and a complex filtered list. TrainLLM addresses this by replacing general scores with an automated pipeline that evaluates models based on specific API conventions. Shifting the focus from mathematical error to behavioral testing ensures the model can handle the edge cases required for a production environment. The process begins with data preparation, where the raw requirements are structured into high-quality training examples. This pipeline implements structured thinking. Instead of training the model to produce a result immediately, it requires a reasoning trace that explains the logic before the final JSON payload is generated. During the training phase, the system uses rank-stabilized scaling. This stabilizes the weights at higher ranks, allowing the model to learn more complex patterns without manual hyperparameter tuning. To manage compute efficiency, the pipeline uses a plateau detector. It starts with a short canary run of only 300 steps to sample the learning curve. By projecting the loss curve forward, the system identifies the moment improvements will stall. It triggers an early stop, cutting the run before it consumes expensive GPU cycles on a model that has already peaked. This combination of structured reasoning and predictive training limits overfitting while ensuring compute resources are spent only on meaningful improvements. The defining feature of the pipeline is its evaluation philosophy. It prioritizes specific technical conventions over a single average score. After every checkpoint, TrainLLM launches a local server to test the model against a holdout dataset that specifically isolates different API patterns. The system categorizes performance by convention, ranking failures worst first. If a model struggles with filtered lists but excels at ID lookups, the dashboard highlights that weak align reasoning. Knowing exactly which behaviors are failing allows engineers to update the training data for the next iteration, rather than guessing why a score didn't improve. If a model retains bad habits, like chaining multiple API calls when one is sufficient, the pipeline runs a preference optimization pass to correct those specific priors. Once the behaviors are refined, the final step is DARE-ties merging, which prepares the adapters for high-speed use. This component merges specialized LoRa adapters into a single, unified model, removing the need to swap adapters during inference. Because the final model is unified, multi-step API calls share the same memory cache, which significantly lowers the latency for complex chained requests. This entire process functions as an automated tournament, where every checkpoint is measured and only the highest performing version is promoted to the registry. The loop closes when weak points found during evaluation are handed off to a synthetic data generator, creating targeted training examples for the next run. This continuous orchestration is managed through a central interface that tracks telemetry, loss curves, and model health in real time. Linking these steps brings the discipline of a software engineering cycle to the world of model fine-tuning. Treating model behavior with the same automated scrutiny as source code is the most reliable way to build intelligent tools for production environments.